This video looks at acid and base strength. By the end of this video, you should understand acid strength in terms of degree of dissociation. You should understand acid-base strength in terms of competition for H+ ions in an equilibrium system. You should understand the relative strengths of conjugate acids and bases. And you should be able to name the common strong acids and bases. One way to think about acid strength is in terms of degree of dissociation. Take this example here, where HA dissociates to form H+ and A-. When HA is a strong acid, it completely dissociates, meaning every single HA molecule comes apart to form H+ and A-, leaving no undissociated HA. Weak acids, on the other hand, dissociate to a much smaller extent. Given this same solution of HA as a weak acid, a very small amount will dissociate to form H+ and A-, leaving a very large amount of undissociated HA. Now let's consider how this applies to the Bronsted-Lowry definition of acids and bases. Take this simplified acid-base system here, where HA represents our acid, H2O our base, H3O+ our conjugate acid, and A- our conjugate base. One way to think about acid and base strength is to think of the bases as competing for the H+. In other words, both H2O and A- are trying to take H+, either from H3O+ in the case of A- or from HA in the case of H2O. If H2O is a stronger base than A-, that means it's more able to take H+. So it will take an H+ from HA, thus causing the reaction to go in the forward direction. The equilibrium position then will lie far to the right. On the other hand, if A- is a stronger base than H2O, it will be better able to take H+. It will take those H+ from H3O+, causing the reaction to go in the reverse direction, and the equilibrium position will lie far to the left. We can also consider the same system from the perspective of acids. Weak acids are able to hold on to their H+ better than strong acids are. In other words, weak acids don't allow bases to take their H+ as well as strong acids do. If HA is a strong acid, it will readily give up its H+ ions. Therefore, the equilibrium position will lie far to the right. If HA is a weak acid, it will hold on to its H+ ions very tightly, thus causing very little forward reaction to occur, and our equilibrium position will lie far to the left. Putting the pieces together then, strong acids are said to be able to transfer all of their H+ ions. This means that the reaction will essentially go to completion, meaning there'll be negligible reverse reaction. This also means that the conjugate base of that strong acid will not be able to take H+ from the H3O+ to cause the reaction to go in the reverse direction. Therefore, conjugate bases of strong acids are incredibly weak bases. Weak acids, on the other hand, transfer only a few H+ ions. This means that they will establish an equilibrium, and usually that equilibrium will be reactant favored, since very few of the H+ were taken by H2O. This also means that the conjugate base of the weak acid has a relatively strong ability to take H+ from H3O+ and cause the reaction to proceed in the reverse direction. Therefore, conjugate bases of weak acids tend to be on the stronger side. This table sums up some of what we've just seen. Notice that as the acids become stronger, their conjugate bases become weaker, and vice versa. As the base becomes stronger, the conjugate acid becomes weaker. It's important to note that strength and weakness is all relative to everything else in solution. Just because we have a weak acid, this does not mean we have a strong conjugate base. It just means that it's on the stronger side as compared to some other bases. Since this is an equilibrium system, we can use a K value to describe it. The acid dissociation constant, or Ka, is the equilibrium expression for an acid-base system. Now this is in terms of the acid. We can also do one in terms of the base, which is abbreviated Kb, but we'll look at that in a later video. Again, consider this reaction here. Writing a K expression, we can choose to express it with H3O+ or simply H+. These are both the same thing. Notice water is not included since water is a liquid and therefore its concentration does not affect our equilibrium constant. Here's a table summarizing everything we've seen so far. Starting with strong acids, recall that our equilibrium position will lie far to the right. The reactions essentially go to completion. Therefore, the H+ concentration will be essentially equal to the initial acid concentration, since all of the initial acid will have dissociated into H+ and A-. Since the equilibrium position lies so far to the right, we can expect very large Ka values. Likewise, the conjugate base A- will be a much weaker base than H2O, since it is unable to take H+ away to cause the reaction to go in the reverse direction. Looking at weak acids, our equilibrium position lies far to the left. This means that the H+ concentration will be much, much smaller than the initial acid concentration, because only a small amount of the initial acid has dissociated into H+ and A-. Therefore, this equilibrium is reactant-favored, giving us a very small K value. Also, our conjugate base will be a significantly stronger base than water, since it is able to take H+ quite well and cause the reverse reaction to be favored. Unfortunately, there's no way to know just by looking at a formula whether or not we're dealing with a strong or a weak acid or base. Therefore, the best thing to do is to just memorize the most common strong acids. Here's a list that you need to have memorized for this class. You can assume that any acids not on this list are weak acids. Likewise, here are some common strong bases. Essentially, any hydroxide of a group 1 or group 2 metal will be a strong base. Again, anything not on this list can be considered a weak base. An interesting note about strong bases, however. While all of these strong bases listed here will dissociate completely in water, some, like calcium hydroxide, have limited solubility in water, so it will only dissociate insofar as we're able to dissolve it in water. Anything that doesn't dissolve, obviously, will not dissociate. That brings us to the end of this video. Let's review our goals. First, we looked at acid strength in terms of degree of dissociation, with strong acids dissociating completely and weak acids dissociating to a small degree. Then we looked at acid and base strength in terms of competition for H+ ions in an equilibrium system, with strong bases being able to take H+ and weak bases not being able to take H+ very well. Then we looked at the relative strengths of conjugates, with strong acids having weaker conjugate bases and weak acids having stronger conjugate bases. And finally, we looked at a list of common strong acids and bases that you should memorize.